Hello everyone, I'm Paul and today we're solving problem 2141, maximum running time of n computers. This is a hard one and here I will show you what I think is an intuitive solution. We are given some number of computers, an integer array batteries, where each battery corresponds to the number of minutes that we can use it to run a computer, and we want to return the maximum number of minutes that we can run all computers simultaneously. And this is very important. We can insert at most one battery at a time into each computer. We can insert and remove batteries any number of times, and we can assume that removing and inserting processes take no time. So if we are given two computers and the array batteries includes 3, we are given this. And here each of these batteries can run a computer for 3 minutes. So we can use battery number 0 for computer 1 and battery number 1 for computer 2. We wait for 2 minutes and then battery number 0 can run for 1 more minute, battery number 1 can run for 1 more minute, and we can change the battery from computer number 2. We change battery number 1 with battery number 2 and wait for another minute. After that minute we get this state, and now we check the battery from computer number 1. We go from 0 to 1. We wait for another minute, and now we can't run these two computers simultaneously because we only have one battery left. These two batteries are at 0. So at this point we end, and we need to return the maximum number of minutes that we can run the computers simultaneously. So for this case we will return 2 plus 1 plus 1, meaning 4. Now, as you can see, this is a game of distribution. And there are at least two ways to solve this. One is we can find the perfect distribution with a greedy approach. And the other one is we can forget about the perfect distribution and try different targets with binary search. Here I will show you this approach because I think it's more intuitive. Let's say that we are given two computers. This is the array batteries. Here you can see a visual representation of this array. And let's say that we're using battery number 2 for the first computer and battery number 3 for the second computer. Now we want to run a binary search to try different results. And for this, for every binary search, we need a low bound and a high bound. For low, if we look at the constraints, we know that we can have at least one battery, and that battery can have at least a power of 1. So low is 1. And for high, we can take the sum of these array batteries, which in this case is 13, 15, 16, and divide 16 by the number of computers. This divided by 2 is 8. So with all of this power, we will never be able to use more than 8 for each of these two computers. So the low bound is 1, the high bound is 8, and the midpoint is 5. So this is our current target. We are checking if 5 is a valid result. This means that we only care about anything that's below this line target. And of course that we are using the largest battery for one computer, and now the question is if we can fill this computer up to this line. And the answer is we can, because here we have a space of size 1 to 3, and here we have 3 minutes available. And if we use all of this power, we can fill this space. So 5 is a valid target, and the result at this point is 5. Now let's see what's happening here. We only care about filling this space. So the question is, how much power do we have in this range? Well, we have 2 plus 1 plus 2 plus the minimum between target, meaning 5, and this power, 11. and the minimum between 5 and 11 is 5. So if we do 2 plus 1 plus 2 plus 5, this is 7, 8, 9, 10. So here, this range, we have a power of 10. And now we can check if this power divided by the number of computers is greater or equal to the target, and this is 5. This means that here we have enough power for these two computers. So as you can see, we don't care about the perfect distribution. We only care about the total power that we have below target, and if this number divided by n is greater or equal to the target, this means that we have enough power for the number of computers that we have. And maybe you are wondering, why don't we also use this chunk? And this is because if we are using this battery for some computer, at the same time we can't use the same battery for a different computer. That's why we avoid everything that's above target. The problem description says that we can use only one battery per computer at a time. And maybe you are wondering, how do we know that we need to use these two batteries for our n computers, in this case 2? And the answer is we don't know. Let's say that we start with battery number 0 for computer 1, battery number 1 for computer 2. And we only care about having enough power for our two computers. We don't care about which specific battery are we using for each of these. So if we start here, we can instantly change batteries in 0 time. That's in the problem description. So we can go to this distribution, for example, and we know that here we have a valid result. So we actually don't care about the perfect distribution of computers and batteries. We only care about this. So now we know that 5 is a valid target, and given that we want to get the maximum number of minutes that we can run these two computers simultaneously, we want to try higher targets. So we move left to mid. So now high is 8, low is 5, and mid is 7. We are rounding up this number. So this is our current target. We only care about anything that's below this target. So the question here is, how much power do we have in this range? Well, we have 2 plus 1 plus 2 plus the minimum between 11 and the target, which is 7. And the result here is 12, meaning here we have a power of 12. And we have two computers, so we do 12 divided by 2, and this is 6. This means that we can use a power of 6 as a maximum for each of these two computers. And given that 6 is smaller than the target, this is not a valid target. We don't have enough power for this target. And given that this is not a valid result, the result stays at 5, and we need to update the high bound to mid minus 1. Now high is 6, low is 5, mid is also 6, so this is the target, and we only care about anything that's below this line. The total power here is 2 plus 1 plus 2 plus the minimum between 11 and the target, meaning 6, and the sum here is 11, and this divided by the number of computers is 5. Given that this is smaller than the current target, this is not a valid result, so the result stays at 5, and we update high to mid minus 1. And now high is equal to low, so now we end this loop and return 5. And by doing this, we are solving the problem in big O of n log m, where n is the number of elements in batteries. Remember that we are iterating this every time to check what's the power at every step, and log m is the range for the binary search. Space complexity here is big O of 1. So with this in mind, now let's go with the code. First, we say that low and high are 1, and the sum of batteries divided by n. Now we can implement the binary search. So while low is more than high, every time the midpoint or the target will be low plus high minus low divided by 2. And we need to round up this. So here we add a +1. And every time we want to get the total available power for the current iteration, we are storing this in this variable available, and for every battery, available plus equal the minimum between target and the power for the current battery. Now, if available divided by n is greater or equal to the target, this means that we have a valid result and we can try higher results. So low is equal to target, else here we need to reduce the target to try lower possible results. So here high is target -1. Finally, we return low. So this is the entire code. Now let's submit this. As you can see, this works and it's efficient. I think that the greedy solution is slightly more efficient, but this is overall more intuitive, or at least for me, and it's efficient enough for this problem. So if you found this useful, please drop a like, subscribe, and see you in the next one. Bye bye.